Good afternoon. Thanks for coming to the session this afternoon. I think it's going to be informative. My name is Joe Pote with CMC Joist and Deck, and I'm going to be moderating. And it's my pleasure to present today's speaker, Dr. James Fisher. He's Vice President of CSD in Milwaukee, and he's also the consulting engineer for the Steel Joist Institute. That's one of those you're supposed to turn off. He is also on various committees with AISC, ASCE, and AISI. I could talk for hours, I'm sure, about all he's done with those various institutes. He has also authored numerous publications on steel design and various aspects of steel design. And I will turn it over to Jim.
The only requirement is I can still get up here, and that's a big step there. Thanks, Joe. What we're going to talk about today is the design of lateral load resisting frames using steel joists and joist girders. This is we're going to talk about a publication that was written this last year, and it was authored by myself with a great deal of help by Perry Green, who is the technical director for the Steel Joist Institute. Is Perry here? I haven't seen Perry. He's probably busy manning a booth or something. And Joe Pote from CMC Joist Company. So I had a great deal of help. We felt that there was a void in knowledge on how you can actually design one-story buildings, both in relative to wind and seismic applications, by using either joists or joist girders. So that was the reason for the development. Dr. Green, I just introduced you. Nice that you could come. Yeah. Okay. That was the reason for the development of this technical digest, and I have a copy here. And I also want you to know at the SJI booth, I think they're going to give away like 10 copies or something. So that's a $530 value for nothing. Yeah. So stop by their booth and see what it's all about. So this is really, I would call it an introduction to what's in this digest, because there's so much there that you really can't do it justice in an hour's time. But this will give you a little flavoring for what's in the digest, and hopefully then you'll get one from SJI if you're faced with this type of problem. Okay. As I mentioned, the purpose was to present information to the engineer of record and also the joist manufacturer for the design of single-story moment-resisting joists and joist girder frames. And you'll understand why we say single-story in a few minutes. What we cover are both considerations for wind and seismic lateral loads. I might add there's two example problems in the digest that are very exhaustive. In other words, they go all the way from looking at the wind and seismic loads down to how you actually design these frames. And as I was reviewing for the talk, I realized how much the practice has changed since I started in the business. It was just, you knew what the loads were. Now, when I look at these examples, half the time is spent figuring out AISC 7 and figuring out what the load is. It's much different than, where I'm from in Wisconsin, it was a 20 PSF wind load. And take 3/4 on the roof. Most of my buildings have flown away by now, by the way, so it's a different world. But there's a lot of time spent, and it's not easy. It's complicated, so it takes time. But that's the purpose. it's limited to single stories, not because of wind requirements, but primarily because of seismic requirements. If you look at trusses or roof joists or joist girders, in general, they are so much stiffer and stronger than the columns that you cannot do the weak beam, strong column criteria like the seismic boys would like us to do. You have strong beams and weak columns. And that is permitted with one-story buildings by the code. So that's why this is limited, at least at the present time, to single-story buildings. But that is the predominant use, as we know, of this material. I mean, most joists and joist girders are in single-story buildings. However, I might mention that there's a brand new specification and catalog on composite steel joists, which is really aimed at the floor systems. Okay, the digest illustrates the procedures to how to analyze, design, and specify joist and joist girder moment frames to resist these wind and seismic loads. We assume in the digest, and you know what that means, that you're all familiar with the 2005 AISC specification. That in itself is a major learning event for many of you. And that you're familiar with the 2005 AISC seismic provisions, and that you're familiar with ASCE 705. So once you get familiar with those, it's time to retire. And then there'll be new ones. One point I want to make, there's no more difficulty in designing a system with joist and joist girder frames than it is using wide flange beams and columns. I think the only added requirement that is very important is communication. There's more communication that needs to go on between the engineer of record and the joist supplier as to specification of items and exchange of information, and we'll talk about that. And you need to be aware of the, as we say here, the interrelationships between the framing elements. And as we all know, the most economical design is one which minimizes manufacturing and erection costs, and one that reduces special requirements like seat stiffeners, cord reinforcing, etc. Same as with normal steel frames. I want to make this point. When you have a single-story building and you're looking at the lateral load system, the last system you want to really use is a moment frame. We're talking about moment frames, but it's the least cost-effective frame system. You really want to look to see if a roof diaphragm system with wall bracing can satisfy the lateral load requirements, because that is going to be your most optimum type of building. And when can't you do that? Generally, it's only when you have long, narrow buildings, when the length to width ratios exceed, say, 4:1 roughly. Then your diaphragm systems get to be impossible to make work, or very difficult to make work. So keep that in mind as we go along here. I'm not pushing moment frames. I'm just saying if you have to do moment frames, then this is how you do them. As I said, we have to communicate with one another. That is, in your design offices, you have to communicate the design data to the joist manufacturer. You must specify the proper loading to the joist manufacturer, and here stiffness data, which is a little different than what you may be thinking about, because remember, you're doing a moment frame, and now the stiffness of the joist or joist girder comes into play as far as how the forces are distributed between columns and the joist girder or joist. What's also very important, not only in this type of framing, but in any building, is the columns and the connections, that you're very clear on how you want the joists or joist girders to frame into the columns, and you need to do that design properly, of course. So you have to have proper communication. The joist manufacturer, once you give him or her these loads, will design in conformance with the SJI specifications and other contract requirements specified by the design professional. And I think we'll talk about a few of those different requirements than what is normal within SJI in just a few minutes. Now, what you're designing here is considered an ordinary moment frame in seismic terms. We always just said moment frames, but when you start talking about seismic applications, then we would call this an ordinary moment frame. And the R value for the system is 3.5. Okay? And we'll mention, whether you should be using 3.5 or whether you should be using an R of 3 in various designs. And of course, the first step is to perform a preliminary analysis. And in general, I would say for one-story buildings, it's good to consider the bases of the columns as pin bases, okay? And then create all the moments or take all the moments out in the joists and joist girders. You may have to use some fixed base conditions to control drift in certain instances. I try to stay away from it myself, especially if on the exterior columns, if they're on some sort of pier or something, you just get into problems with development of the moments at the pier locations. Interior footings, it's not so bad. Of course, after you do a preliminary selection of the columns and joists, you do your computer analysis or a hand analysis, if anybody's still doing that, to determine forces, moments, and deflections. Now, you notice there in parens, both first order and second order. I think that you are all aware now that the AISC 2005 specification, which is adopted by the 2006 IBC, requires a second order analysis on all steel structures. So you must do a second order analysis. Now, some people get all excited about that, but for most people today, it's you push that button that says second order analysis, right? Now, there's some things you're supposed to do, and that we have to do now because some of the software vendors haven't caught up with what the specification wants you to do. And that's explained not only in this technical digest, but AISC has done a good job of trying to educate people on this issue. And there will be a design guide coming out by AISC shortly on how to handle second order effects. One thing that's a little different here is that as soon as you say you have to do a second order analysis, that's a nonlinear problem. So your analysis must be made for each required load combination. You can't do an analysis for dead load, live load, wind load, and add those up. It has to be for the required load combination because it's nonlinear. Which means that when you go to specify loads and forces to the joist manufacturer, any moments you develop, for example, in your analysis, you have to give to them for each load combination. Not load case, but load combination. Okay? Now, what we recommend in the technical digest are a couple of different models for analysis. The first is what we call Model 1 in here, and it's to get the behavior of the frame both from a strength point of view and a stiffness point of view, that is, how much drift you have in this particular frame. And for the most part, it's accurate enough to model the structure by going to mid-height of the joist or joist girder, assuming a prismatic member, and use an equivalent moment of inertia and area that represents the moment of inertia and area for the joist or joist girder in that frame. And you'll notice that that's represented by the dotted line there. Most of you may know this, but the trial joist stiffness can be attained from the SJI equations in the catalog. There's two equations, one for LRFD design, one for whether you're doing ASD design, and they're shown on this slide. And you just simply, if you have a joist girder, for example, N is the number of panel points, P is the load at each panel point, L the girder length, and D the girder depth. You substitute in the equation, and you have a moment of inertia that gets adjusted by about 15% usually because of web distortions. There's also an equation in the catalog. If you have a joist, you can find from the load tables an equivalent moment of inertia. So it's not a big deal to get what the, for preliminary sizing, what the moment of inertia of the joist or joist girder is. Another thing in this catalog is a table that I think you'll find useful. And I know as a designer, one of the complaints we always have to the joist manufacturer, Joe, where'd Joe go? Here back, you know, and you hear it all the time. Well, I don't know what the size of your members are. I don't know what your chords are. I don't know how wide they are. I don't know how thick they are. I don't know what they are. Hopefully they're steel, okay? And they're 50 KSI. We know that, all right? So when you're looking at some of this material and you look at a moment, let's say you come up with a moment and you say, gee, I wonder what the size of those chords is going to be. This table is very valuable because if you find the force in the chord, okay, moment divided by depth, okay, the table goes all the way from 6 by 6 by 1 inch angles down to 2.5 by 2.5 by 3/16, and the values listed here are the axial loads. This is an LRFD table, by the way. The axial loads that two angles can carry with the unbraced lengths that are shown, and then the area is given. So it gives you a way of getting a quick look at what the angles are going to be, and then if you later on, if you know the angle size, then you can also calculate a moment of inertia. Okay, so that's helpful information. The reason that's there, and the reason I put it in the catalog, is that the 2005 AISC manual does not contain tables for two angles 50 KSI material. The 9th edition manual did contain that, but it was dropped out of the 2005. You only have A36 material for the angles. So I used to go to the 13th edition and look up those strength, but since it's not there, I created these tables. Now, there'd be other ways to do it. You could divide your LRFD moments by 1.5 and go into the ASD tables if you wanted. But this is more convenient. Yes, sir?
Where's that table located?
This table that the question was, where is the table located? It is in the technical digest, okay? Or it would take you an hour on an Excel spreadsheet to develop such a table, okay? The second model, we've got one model that we look at for the drift and initial sizing. Second model is what we call Model 2, is shown here. And as you know, in seismic design, you have to have some sort of fuse, that's going to go. And in this case, since we have weak columns, the requirement is that the column will develop its M sub P. Okay, and that's for the seismic design. So if the column is the fuse, then we need to know in the final sense what forces are going to be in our joists or joist girders in the moment frame for these fuses of M sub P. And what we do is we use the AISC specification, and we say that, okay, the moment is 1.1 times RY times MP. That's the requirement for the connection. That's the requirement that we put on the joist girder frame. So this model simply indicates you're saying that each one of these columns is going to develop MP, and you apply that basically to a continuous beam model and get your moments in the joist girder system. Now, the moment really is M sub P at the bottom chord of the joist girder. Okay? So we extrapolate that up to mid-height by the ratio of the length to the mid-height over the length to the bottom chord. So you put that in this model, and that'll give you what moments will go into the joist girder for that load condition. Now, since, I should never say this, but we learn every day. Since writing this, I realized that probably the quickest way to get a preliminary design and get the stiffness of the joist girders is to do a quick preliminary design on the columns, okay? Then just look up their M sub P, okay? And then that really is going to be the moment at the two, in this case it's a 3-span, it's going to be the moment at the 2 end spans on the joist girder. So I can quickly get what's the requirement as far as the moment of inertia for looking at, say, drift and the other load combinations. This just shows what that particular moment diagram would look like. So you can see the center joist girder, the MP moment gets distributed left and right, and it's basically half MP, but the end spans get the whole moment thrown at them. Another thing I want to mention, and some of the old timers in here, like me, have a lot of buildings designed where we never thought about what we call the leaning columns today, right? Because we just didn't. We didn't think about it. We should have, whether we were doing ASD or LRFD, doesn't matter. We should have thought about it. What that means is, and I think an easy way to explain it to those of you that haven't thought about it, is if you have a big box building, and let's say we're not even talking moment frames, you have a tilt-up wall job, and you're figuring out the diaphragm forces into the walls. And you basically have post and beam columns everywhere in the building. Okay? We used to look just at what the lateral loads were and take those over to through the diaphragm into the wall system. Many people did. But think about it. The columns are not straight. Every column needs a brace. The diaphragm's bracing the top of the column. Every brace has a brace force, and those forces can accumulate. That's another way of looking at P delta. As it sways and you have an axial load, it's trying to overturn, you need a resisting force. Now, that can be a fairly sizable load if you have a big building, lots of leaning columns, and it sways a lot. Okay? So that is required in your analysis to consider these leaning columns. I'm not nearly as fast as the younger fellows in the office using the computer. So if I have to do this and can't give it to somebody else to do, I do a two-dimensional model rather than a three-dimensional model. And this just shows a typical way to do that with a two-dimensional model. Well, they gave me this pointer today, so I should... Ooh, I already lost my pointer. No, I didn't. I found it. An easy way to do this is that we put what we call a pseudo column in here and a pseudo column over there. And on that pseudo column, we put all the vertical loads that are represented by the interior leaning columns. Plus, you can put on, if this is a heavy wall system and you're looking at seismic loads, you can put on the loads from the wall system. And I don't know, there's probably plenty of West Coast people here. There's probably plenty of East Coast people and Midwest people. And I know what you're all going through now with the seismic requirements. But it's amazing to me the difference when I compare a tilt-up wall job with a light metal panel wall building with the seismic loads. The wall weights have a significant effect on the seismic forces, and I think we're going to see a trend sometimes to some smaller or lighter wall systems again, because those seismic forces are very large if you have the tilt-up or precast load systems. Okay, so that's just a way of handling that in a model, or you can do a three-dimensional model, and that works fine. Now, also shown in the document are the typical connections that we use. This, of course, you're all familiar with. It's the standard or basic connection where there's really no design of the connection. There's the joist girder sits on top of the column. Joist sits up there. There's a stabilizer plate. We got the necessary holes for OSHA, both here and here and here. That connection, of course, is not able to develop much moment capacity at all. So it's not recommended for these frames. You can do things in case in the light of wind loads, for example. You can stiffen things up, again, to eliminate bending in the cords, and that's just, those connections are shown in the book. One that I've used with success on wind frames, not seismic, but wind frames, is shown here. What I often do on these buildings is I'll use the perimeter columns as the moment frame columns and leave the interior columns as leaning columns. Put all the moments in the sidewall columns, for example, and the first joist girder that frames into them. And why do I do that? Is because I've learned it from my friends in the metal building industry. That's how they design their frames, and they know what they're doing, okay, to get an economical frame. So one connection, if your moments aren't too great, is to simply have a special seat here on the joist girder where you spread your bolts out so you have some moment capacity, okay? And that works very effectively. You can think of it, if you have a little problem thinking of it as a moment connection, just think of it as an end plate. You got two end plates. You've got one on the top of the column, and you got an end plate on the seat. And if you give the manufacturer the forces here, they will design that seat to take those forces. Okay, so that's very effective if you use perimeter columns. And it's only good for a certain amount. I think it's roughly, if this force is roughly 50 kips in the cord, it's a good connection. If it gets more than that, it gets a little out of control. In which case, we switch to what I would call my favorite connection, is where you take the girder off the top of the column, you put it on a seat, either stiffened or unstiffened, and you then weld a plate to the cap plate of the column and weld the plate to the top cord of the joist, or joist girder. The reason I like that is I'm not depending on the joist girder supplier for anything other than take the moments. I don't have to have them do anything special, okay? So this is very effective. Now this connection works well for seismic applications as well. And that connection has been tested at Georgia Tech by Professor Leon for all the cyclic and hysteresis loop kind of requirements, and it works well. And the reason we get all excited about this, because if you just have a force here, of course you have an eccentricity P times E, and that moment in the top chord of the joist or joist girder, it just can't handle it. The two angles are just not strong enough to handle much moment. So that's why you have to eliminate that eccentricity by some means. Here's the same connection for an interior column, and you see we have truly, as soon as we weld here, weld there, and we weld down here, we have created continuity. So we do have a continuous girder system, and of course those moments have to be given to the joist girder supplier for proper consideration. And if you want to throw moments into the column, then certainly you can weld to the column cap again, right there, and transfer whatever moment you need into the column. Just a few words about the specification of required forces and moments. This is just an example with some dead load, live load, and a snow load, very light snow load, and wind uplift. And these are things that we'd like to see you put on your drawings to give the girder supplier or joist manufacturer information that they would like to know. They would kind of want to know if you did it right too, okay? And so we'd like you to say, okay, I've used the following combinations, load combinations. These are my loads. These are my wind uplift loads. Here's my seismic criteria for the building I'm using. Notice that this one says R of 3.5, and it's ordinary moment frame. Gives S sub ds and S sub d1, a rho and Q sub e, for example. And you would also indicate what minimum moment of inertia you want on that joist or joist girder. Because remember, you've done this indeterminate frame analysis, and you need to specify what you want. Now, you might say, well, what if the joist girder manufacturer comes back and has a larger moment of inertia than the minimum? What's that going to do to you? Nothing. Really nothing. Because the columns aren't going to get any more moment than M sub P, and nothing changes there. So I don't think it's too critical. The drift may get reduced because they've used a larger moment of inertia. But basically your analysis is going to be okay, and you don't have to redo it.
Depends on to what extent your loads are on the slope part of the spectrum. You end up with a stiffer building than you were assuming.
From a seismic point of view, yeah, it could change the period of the building slightly, but probably not significantly. You could also give a range, and that's why a good preliminary design is good, and get the information to the joist supplier right away. Yes, Joe? I'm sorry. Was there a question? This gentleman asked, depending on drift criteria, wasn't that the question?
If you're on the descending part of the spectrum.
Of the seismic, the response spectra. If you're in the descending part, it can change the period of the building, which can change the forces. So it is important, but it's a fairly minor thing generally. Okay? Thank you. And then we might also specify a minimum top chord width, for example, because we want to have room to weld whatever plate we've designed. So you can do a downhand fillet weld. Joe, do you have another comment? You look perplexed. Yes.
If your inelastic moment is what's controlling the system, then yes, the moment of inertia in this partner doesn't matter. But if it's not what's controlling, if a wind moment is controlling, or if you're in a B or C seismic category, then a higher moment of inertia will draw more moment into the joist girders, which is then
Yeah, I think since we're being recorded, what he's saying is if you're not getting this M sub P business at the column, but if a wind load was controlling and you used a larger moment of inertia, okay, it would certainly change the drift, but it would also suck more moment into the joist girder than what you might have specified originally. Is that in essence, Joe, what you're saying? So I think the key is that we should try to get the moment of inertia that the engineer has specified, or be darn close. And I don't know what darn close is. Let's just say among friends 10%, okay? And then if you wanted to rerun it, you certainly could. So it could be a little iterative thing if your prelim hasn't been too good. Okay, so that's where this communication comes in a great deal. That's the hard part of this, is that you don't really know precisely what moment of inertia the manufacturer is going to use. But using that chart I showed you and a decent preliminary design, you're going to be really close. Yes, sir.
All right, well, assuming that the column is thin at the base, that assumption in itself is much rougher than what we're talking about.
Thank you. The comment is, we assume a pin base, and actually there's going to be moment there, and that's going to change things anyway. But we're all happy doing that, right? Yeah. So thank you. John.
Yeah, the only thing I was going to point out, in a one-story building, I mean, the moments aren't really going to change if I've got a base, whether it's, no matter what the stimulus is.
From a lateral load.
Right, from the lateral load. For gravity load, yes. But, and that's it. And just...
Yeah. Thank you. Okay. Some other things we want to see specified, and these are all outlined in the technical digest, are the loads, and of course we give the splice requirements and the loading combinations. We've suggested a few tables in the document, various load combinations, and these may not be all inclusive, but they generally are the ones that control. And as you all know, there's so darn many today that you can go crazy with load combinations. And I'm inclined to say the way we ought to look at structures today, you ought to look at 2 or 3 load combinations that you think are going to control based on your judgment. Run those and see how your structure's behaving. See if it's strong enough. And then push the button for the 10,000 load combinations that the code requires, and then peruse that. Because otherwise, the tendency is if you get all these load combinations out of your computer output, it's so overwhelming that you don't look at any of them. You just believe what's coming out. And that's not a good way to approach this. So this is just an example, the panel load, the left end moment, right end moment, any top chord extra forces. And here's another suggestion. Again, this is in the digest. And we also suggest a type of table that you could use to show the various wind uplift criteria and forces on the joists and joist girders. Remember that you as the engineer of record have certain obligations if it's seismic design requirements. The ones in yellow here you need to indicate on your drawings. You have to show the designation of the seismic load resisting system. You have to say what it is. And you have to designate the members and connections that are a part of that system. And you have to show the configurations of the connections and the connection material specifications and sizes. Since we're an ordinary moment frame, I don't believe there's any locations of demand critical welds. There's no protected zones like in other systems. And the one place where I failed to mention it, but the SJI has taken the position that they will design the girder moments, not just for the wind and seismic moment, but they'll design the whole girder for the 1.1 RY MP. They want to guarantee that the girder stays elastic. So we put extra moment into it. Okay? And I think that's important. The other thing is that any cord splices will meet the requirements of Appendix W. Or was it D 1 point, what is it now? 8. Yeah. So those splices will meet those requirements. The web members will be designed in accordance with the SJI specifications. Just a comment, that again promoting the idea of using R equals 3 if it's a seismic application. You shouldn't use 3.5 and subject yourself to special inspections and special connection requirements if it's seismic design category B or C. We really recommend that you use an R of 3, just as AISC does for moment frames. Yes, sir.
A question. If all the elements in a girder are slender elements, that means 100 or something like that of slender, they cannot arrive to yield in completion. It's absolutely impossible. So we cannot speak about inelastic behavior. So R must be 1 because we don't have inelastic behavior.
No, I think it's permitted in a single-story building, okay? We're guaranteeing that the girders will stay elastic. They will not go inelastic in the seismic event. So we can use R equal 3.5. The column will become the fuse. But we have to make sure that the girders stay elastic.
You mean that the individual parts of the girder do not buckle?
Well, yeah, they can't buckle, right, for the loads. And we've put on these end moments that you not only have your vertical loads that may cause the size to be a certain amount, but also the end moments which are designed for 1.1 RYMP.
Which means that the girders, we're not talking about the girder going inelastic by a part of it yielding.
No, we're never talking, the girder remains elastic under all load combinations. So I believe we can use R equal 3.5. Yes?
Do you need more bracing to be able to do that?
I don't think you need more bracing, but you need proper bracing, okay? You have to make sure that the bottom cord or top cord of the joist girder is not going to lateral buckle, okay? And there is a whole chapter in here on the bracing requirements, which really is the same as what comes out of AISC 2005 spec Appendix what, Larry? 7. No. 6. 6. So that is discussed. In fact, I have one slide that shows it. There it is. That's just what we think it would be a good example to actually, make sure you aren't doing something too flexible. But if you have a joist going to a joist girder, it's my view that the joist manufacturer has to design this bracing. He's the person that knows where the braces have to go, and he has to figure out the strength and stiffness required. Usually it's not a problem with the joist. There's enough stiffness, so the forces aren't too bad. In the digest, I do 2 examples. This is the building. It's basically 240 feet long and 120 foot wide, sort of a, just a box. It's got interior columns. Notice that it's the 3-span condition I showed before. And each line is a steel moment frame. And that is the cross-section of the building. 1/4 on 12 roof slope. I never noticed this before, but the center girder says no slope. Can't have that. As you all know, the IBC 2006 requires what? Minimum roof slope of 1/4 on 12. Yeah, we got tapered insulation. Yeah, we got tapered insulation, or we got the camber. Okay, no. We would use the tapered insulation to get, let's say the drains were at the columns here, okay? We would have to have a cricket. And, oh, thank you, John. I'm saved. So that's the frame. Now, example 1, I took as Charleston, South Carolina. Anybody here from Charleston, South Carolina? Bless you guys. You're in the worst part of the country, right? Yeah, you got the worst, you got the bad seismic, you got the bad wind. What do you have, good-looking women, or what do you have there? I don't know. But you guys are in trouble. And I took a building in Charleston, South Carolina that had precast concrete shear walls and a non-load bearing. And here's the loads. Well, they don't have much snow there, that's one thing. So they don't have a lot of drifting, okay? Here are the dead loads for the building. And there's some collateral load, sprinkler, some mechanical. Live load is 20 there, reducible to 12 for the main members. Ground snow there, that's a lot. 5 PSF. What did we have this winter? We had over 100 inches of snow in Milwaukee, Wisconsin. It's not over, is it? No. I remember twice in my life, recent life, May 5th, 6 inches of snow on the boat opening day of trout season. Yeah, you don't want to go. So that's that's the snow load. Wind load, 120 miles per hour. Exposure C, it took. Seismic load is seismic design category D for the building that I selected. And I use a serviceability requirement with a maximum drift of H over 100 for the precast walls based on a 10-year wind. Example 2 was everything the same as gravity loads as example 1. I did that on purpose. It's a building in Mississippi, and it had the same wind loads, 120 miles per hour, exposure C, but it's seismic design category B versus D, okay? And same serviceability requirements. And I thought this would be really interesting to compare the two. The first one in Charleston, the wind-based shear was 22.9 kips per frame line. That's with the 1.6 factor on it. The seismic-based shear using R equal 3.5 was 49 kips per frame line. And example 2 in Jackson, Mississippi, wind-based shear the same. And the seismic-based shear, using an R of 3, since it's design category B, was 14.3 kips. Notice the difference in magnitude of the moments in this little building, just based on the seismic criteria. What is it? Almost three times as a larger moments, which means much bigger columns, more connections, bigger girders. This just happened to be what ended up being required. I believe all this stuff's in your CD that you got also for the conference. So this was the size of the plates and the connections that were needed for the exterior columns. And in the one in Charleston, South Carolina, I had to engage the interior columns in the moment frames as well. I couldn't make just the perimeter columns work and be decent. The wind shear was just too big. So that was the center columns. And example 2, and you'll see this when you look at, when you go home and you study all the materials that you picked up at the conference, right after you submitted your CEUs. The second one had post and beam columns interior. And just as an example here, for example 1, the one in Charleston, exterior columns were W18 by 86s, interior 18 at 97s. Total column weight 12,000 pounds, girder weight 6,300 pounds, about a total weight of 18,500 pounds per bay. And example 2 came down to about 12,000 pounds. So a fairly significant difference. I think that if I lived in North Carolina, I'd be putting up posters that say, move here, you know, build here, it's really cheap. So I'm kidding you guys from Charleston, of course. Okay, so but there is a major difference. There's an appendix that has a complete design for all this, how you got the wind loads. I went step by step through AISC 705 and step by step a roadmap through the seismic criteria on what to do, how to go to the website and do everything that you have to do. And just an acknowledgement, Joe and I and Perry want to thank the what's called the Engineering Practice Committee, chairman who is sitting here, for their help on this document, and also John Rolfus, who piped up and back, one of my partners who helped me a great deal with the document, and also Jim Malley from Dagenkolb, who reviewed the document for us and basically gave us a nice blessing. So thank you very much. I promised I would be out of here by 4 because they got another group coming in. If you have other questions, why don't you just come up and ask me? How's that? Thanks for coming.